The principle of a profilometer is quite simple. A microscopic tip, in contact with the surface, is moved along the x-axis. The vertical movement of the tip, due to the surface relief, is captured and amplified. The profilometer is generally installed on a z-column, allowing the stylus to be positioned above a part to be measured. The traverse unit moves the stylus along the x-axis, perpendicular to the z-axis. The granite base serves as a reference plane, and as a support for the parts to be measured. More precisely, the sensor slides on a reference bar, thanks to a drive screw, driven by a motor. The bar serves as an internal straightness reference. It is an expensive element, ground with great precision, which often justifies the price of the profilometer. It allows the stylus to record the entire surface texture, be it roughness, waviness, form deviations, or even the form itself. There are also profilometers without internal reference, whose stylus is equipped with a skid resting on the surface, as we will see later. The profile is therefore measured, by pulling the tip over the surface, at a speed chosen according to the roughness of the part. The speed must be moderate, so as not to risk bouncing the stylus, or damaging the surface or the tip. Some modern profilometers allow the tip to be raised and gently lowered to the surface. The stylus itself is terminated by a tip, consisting of a microscopic sphere of a few microns in radius. This sphere, often made of diamond, or a hard stone like sapphire, is attached to a conical support. The whole constitutes a conospherical tip. By default, the tip has a radius of 2 micrometers, and the cone has an opening angle of 60 degrees. But manufacturers offer many models of styli, with various characteristics, especially regarding their length and height. The stylus rotates around a pivot. The opposite end of the stylus is connected to a transducer device, responsible for converting the vertical movement of the tip into an electrical signal. There are different transducer technologies. The most common today is an LVDT inductive sensor, where a ferrite core moves between two coils, fed with an alternating current. The movement of the tip changes the impedance of the coil, which alters the frequency of the current, thus allowing a measurement of the relief. Alternatively, some sensors are capacitive. The opposite end of the stylus has a pad that passes between two electrodes that produce an electric field. The movement of the pad changes the capacitance of the capacitor, in proportion to the height of the relief. For entry-level devices, including small workshop roughness meters, the transducer is piezoelectric, and like the pickup on a vinyl turntable, it creates an electric current depending on the pressing force on the piezoelectric element. Finally, for high-end and high-precision profilometers, the height variation is evaluated by a laser interferometer. This allows for large vertical excursions, while maintaining extreme resolution. Today, the measured profile is fully digital. As the sensor moves, the electronic samples points at a given frequency, i.e. the altitude is converted to numbers at a given time interval.
The surface profiler consists of two main parts: the alpha step scanner and the computer that processes the data. Before and after using the surface profiler, we need to record the relevant usage information in the logbook next to it. First, we need to turn on the alpha step and start the computer. Enter the password wheeler to unlock the computer. Start the corresponding program. Then use tweezers to take the sample to be tested out of the box. Place it on the testing platform and close the lid. Click the Go to Origin button to move the sample to the detection area. Click the down button to adjust the position of the Z stage, so that the probe used for detection quickly approaches the sample. Release the button when the outline of the sample can be roughly observed. Click the focus button, and the system will automatically and slowly move the probe closer to the sample to determine its initial position. By clicking or long pressing the up, down, left, or right arrows, you can adjust the position of the sample along the x and y axis. In some cases, angle adjustment is required, and we can slowly rotate the detection platform by hand. Under the Scan Parameter tab, we can adjust the scanning parameters, mainly the following: speed, length, range, and stylus force. Speed is generally selected at a low speed, because it can obtain more reliable experimental data. However, in some cases, you can also select a high speed for preliminary scanning to view basic trends and location information, and then perform a slow scan. Length is freely defined according to your needs. Range needs to be selected based on the expected height range of the sample, and the range should be slightly higher than the predicted height. Stylus force defines the force applied to the probe during scanning. Select the force based on the sample. For polymer materials, a small force is generally selected. Click the Scan button to start scanning. The scanning speed should not be too fast. Otherwise, the large height step will damage the probe. Therefore, it takes some time to wait for the scan to complete. We can adjust the position based on the initial scanning results, so that the position to be scanned is in the center. Scan again. Real-time displacement shows the real-time height change during the probe movement, which can better reflect the actual situation. It is important data and can be saved according to we needs. After the scan, we get the raw data as shown in the figure. Move R&M to a theoretically horizontal position. And perform leveling. At this time, the two planes will be at the same height. Drag R&M to the two planes to detect thickness. In the delta height area next to it, we can see the height difference between the two planes. We can save our scan results after the scan is complete. In some cases, we can also take screenshots. After use, we should close the scan result window. If we need to scan another point, we need to lift the probe again to prevent it from colliding with the sample during movement. Move the probe to the target position. Focus it. And then repeat the previous operation to scan. After use, click Load Position to make the probe rise to the highest point, and return the detection platform to the loading area. Use the tweezers to remove the sample from the test platform. Keep it properly. and close the lid. Finally, close the programs. Turn off the machine power and shut down the computer.